Okay.
I feel like the light is a big part of everything. Light is shiny colors.
Can you do it? Thank you. Appreciate it. All right. Emag. Before I start, any questions at all regarding home? Yeah, I knew it. Go ahead.
Question 6.43. The incidence equals.
Go ahead. 6.43.
Yes, sir. Electric field incidence equals 10 cosine 2 pi times 10 to the HV minus beta 1z. The A expression is incident from air onto a copper conductor by the instantaneous expression for the reflected electric field intensity.
What? They want reflected?
They want instantaneous expression for the reflected electric field intensity. Yes, sir. And then the SWR.
Standing wave ratio. All right, let me go through this with you. Pay attention to this now. When we talk about standing wave ratio, it's the same expressions we used back in the time you did transmission line theory. You all remember that class? Once you had the reflection coefficient, the standing wave ratio is the ratio of the E field maximum in the region divided by the minimum E field. But this minimum E field, these are averages. These are the average. Remember how when you have an E field expression, you have this, right? You all see it goes through a zero. A cosine waveform has a maximum of 1, a minimum of -1, but it goes through a 0. You understand? So the minimum of that is 0. I should say is minus whatever E naught is. When they talk about this expression, they're talking about the ratio of really the maximum and minimum average value. Now let me just mention this once. If you have, for instance, region 1 here, region 2 here, and you have a wave coming in this way, some of it reflects, right? Then if you looked at the envelope that the maximums were contained in, you would see this. Something like that. You all with me on that, class? This would be the minimum, that would be the maximum of the superposition of the two. Do you all follow me in this class? How many understand this? Just like it was when you did transmission lines, right? So the standing wave ratio is this. It can have a minimum value of 1, and that's when everything is transmitted, nothing is reflected. It can have a maximum value of infinity. The way we get this is just the standard equation used before. 1 plus the magnitude of the reflection coefficient, or 1 minus the magnitude of the reflection coefficient, just like transmission line theory. How many remember that from transmission lines? If you don't, refresh yourself, because transmission line, all the general concepts in transmission lines are also applicable to any kind of plane wave reflection transmission. And you're going to see that with filter design pretty shortly. So that's it. Now, how do you get the reflection coefficient is the next thing, right? That's an obvious one. You need reflection and transmission. You need reflection to get the reflected field's magnitude, correct? Well, the reflection coefficient is something you have to know. In general, it's A to 2, the region, the characteristic, or the intrinsic impedance of the region you're going into, minus the intrinsic impedance of the region you came from, over the sum of these two. Now, the reflection coefficient values are limitless. They can go from minus infinity, theoretically, they can go from minus infinity to infinity. In general, when you look at this, actually they can't really do that. Normally, when one of the two is much larger, say A to 2 is much larger than A to 1, right? Then you're really going to get 1 over, but you're basically going to get A to 2 over A to 2 over 1, right? Now, if A to 1 is much, much larger than A to 2, then you're going to get minus A to 1 over A to 1, or minus 1. So that's sort of the limits, but there's tricks you can play to get things a little larger. And just for now, I'm going to limit us to plus and minus 1 as the main thing. I actually think about this, and I mean, there's people that really are, they're thinking about exotic materials that will make all sorts of things happen, but for now, it's -1 to 1, and it can have an imaginary component, so the magnitudes is what you're worried about. That generally has a magnitude and an angle, so it's gonna be at an angle theta, the deflection coefficient. When you're talking about a strict real number, the angle is 0. That's the thing. Now getting back to this, so we've got air over here and we've got that. That assumes that epsilon relative is just 1 and U relative is 1 if it's not stated. For air, you're dealing with eta just being equal to eta naught, and that would be eta 1. And eta naught is just 120 pi, right, ohms? Correct, class? Everybody with me? Who asked this, by the way? Okay, are you good with it? All right, now let's go get eta 2. If you don't mind, I'm going to put it right here. Eta in region 2 is equal to the square root. The general equation is J omega mu over sigma plus J omega epsilon, correct? Now, we're going into copper. What does it feel? Copper, good conductor? One of the best, right? I'm not going to bother proving it, but the J omega epsilon here is almost, it's useless, so get rid of it. So that's the intrinsic impedance in region 2. I know it's going to have a 45-degree angle. The reason I do is that J is really e to the J pi over 2 or 90 degrees. The square root of that means e to the J 45 degrees, or pi over 4. Follow me? So I know that's the angle. The value I don't know. So now we go here, and you can all see that the omega here is just 2 pi times 10 to the 8. And that's radians per second. Y'all see that? What's F? What's the frequency, class? 10 to the 8th, right? Hertz. So we know that off the top of our head. Now, they didn't put a mu other than mu relative, right? Is equal to 1, or they didn't even state it, correct? Or I didn't state it.
Doesn't state it.
Then, if it doesn't say, you assume the most likely value, which is mu relative 1, epsilon relative 1. That being the case, what is this going to be? It's going to be J times, I'm just going to leave it as omega. Mu will be simply mu naught over sigma, and that's 5.8 times 10 to the 7th for copper. So what do you get for that? It's going to be really small. Anybody? Don't do this in your head, all right? Use a calculator. Y'all got your calculators up. I couldn't hear you.
You want him to pull it for us?
Yeah, please.
3.2.
Go ahead.
45 degrees.
Is it really 3 at 40? I know it's going to be 45 degrees. The magnitude is 3.29, not less than that for copper. Well, maybe you're right. Because mu naught is what? 4 pi times 10 to the minus 7th, right? Mu naught is 4 pi times 10 to the minus 7th. That's going to be a lot smaller than that, I feel.
Omega's what? 2 pi 1 to the 8?
I just want an actual number, not pi's. If you don't mind. Can you read it?
It's small number.
Yeah, I know.
It should be small. Oh, okay.
Anybody?
0.00369.
0.003.
69.
Okay, we'll leave it at that. It's really what? It's 3 times 10 to the minus 3rd. 3.69 times 10 to the minus 3rd ohms. That's about zip. Compared to 120 pi, 377 ohms, it's about zip. So what does that mean the reflection coefficient is? Let's get it. Now I put eta 2 in here, this, whatever it is. I'm just going to leave it as eta 2 minus 120 pi over eta 2 plus 120 pi. How many see I can just put 120 pi down here? That other thing is so small it's insignificant. Y'all with me? 120 pi plus this is 120 pi. All right? Add 0.00369 to 377. Not much difference. So what do you get for it? Isn't that just minus 1 about?
Yeah.
Guys? Yes, you're right. But understand why? Because the other number is insignificant. So it's minus 1. That means the reflected field, now that's in the time domain, right? Let me write this in the phasor domain. Make sure you know how to do this. This in the phasor domain would be EI equal to magnitude of 10, e to the minus j, beta here we can get. I'm going to leave it as beta 1, and I'll get it in a second, z, and it's in the AX direction. That's in the phasor domain. How do I get beta in the first one, by the way? Beta in region 1.
That value over root 2.
What value?
The one right above it, 45 degrees on it.
No, that's
Oh,
eta,
that's
not beta.
omega.
Omega
No,
over beta.
It's,
You're right.
he said it
Equals
right.
C over omega.
It's omega, what?
It's omega over beta equals C over the square root of epsilon r. Is that right? It only
Yeah,
equals that, that's how you find it.
pardon me, what did you say?
I have omega over beta equals C.
Is the velocity, right?
Right, equals.
What he's saying is this, omega over beta is velocity. In air, it's C, right? So this is C.
C over the square root.
Therefore, B is omega over C, right? For region 1, because it's air, correct?
Yes, sir.
Well, what is that? That's this, 2 pi times 10 to the 8th divided by 3 times 10 to the 8th, or 2 pi divided by 3. That was my point. You all see this, class? So this is 2 pi over 3. And that's radians, by the way, per meter. It is not degrees per meter. So we could put that in there. Now to get the reflected field, and let me put that right here. The reflected field is just going to be the reflection coefficient times the incident field. And then it's going to be e to the plus j beta 1 times z in the AX direction. Why is it plus j beta z, not negative, class?
It's
Now traveling the negative.
Reflected implies it's going in the minus c direction, does it? Correct? And that's in region 1. So you've got beta 1. Now this is minus 1, isn't it?
Yes, sir.
So that's really minus 10 e to the j, and I'll just put down 2 pi over 3 times zax. I want to tell you one thing just so everybody knows this. If you don't like negative signs, you can get rid of that negative sign and just add pi or minus pi to that argument. You follow me, class? But you can leave it in there. That's the reflected field. What else did they want?
The standing wave ratio, and then also I was wondering how to get the transmission coefficient.
We'll get that in a second. Standing wave ratio, well, we've got the reflection coefficient of minus 1, about. Now, if you want the exact value, then you've got to go in and put 82 in right there, and you're going to get something that is just about minus 1, but it's got a little lag. It's got a little something else to it, follow me? Then if you wanted the exact standing wave ratio, you would put that magnitude in here, and then you would get something that is going to be very, very, very large. Do you follow me? The minimum this can be is 1, the maximum is, the limit is infinity. So this is tending to a very large number, just about infinity. Everything is almost reflected. Not quite everything, but almost. Are you with me in that, class? Now, how do I get the transmission coefficient? Here you actually need that dinky number right there. All right, now what people say, well, add 1 to the reflection. Well, if I rounded the reflection coefficient, I get zeros transmitted, and that would be true if it was a superconductor. It was perfect in every way, but it's actually not. You do get some field transmission. So now you need the transmission coefficient, and that's 2 times eta 2 over eta 2 plus eta 1. In our case, eta 2 is small, so much less than eta 1, you can say this is about equal to 2 eta 2 over eta 1. Or really, it's 2 times this number divided by 120 pi. Do you all see what I'm doing here? And the transmission coefficient is going to be very small, about 10 to the minus 6 kind of numbers. Just do the math on that and you can see that. Huh?
10 to the minus 5.
10 to the minus 5. All right, 10 to the minus. It's so small, it's not worth talking about. Do you all agree with that, class? What else do they want?
That's all.
Does everybody else understand that? Any other questions? Here's what I'm up to today, doing TM, all right? Did you have a question, sir? No. No? I want to make sure, no, in the far back, I thought I saw a hand. And by the way, it's dark, kind of, I don't see everybody in that back row clearly up here, so. If you got a question, make sure I know you got a question. So, are we favored in the game? Against Tulane or not? Anybody look at the
I think we got like a 19-point spread.
19? I hope they're right. Any other good games this weekend?
I think Clemson. Yeah.
Who? A&M and Clemson.
Yeah.
Oh.
And LSU Texas as well, I think, is the other big game.
LSU, Texas.
Yeah. I think they're like 6 and up.
Clemson almost beat, I'm sorry, Texas almost beat Clemson. Almost. That's the operative word, almost. Nobody cares about it. All right, now we're going to do TM. People, this is important. You will be tested on these things. Can I help you? All right, TM mode. It's transverse magnetic. Here's what it means. Before we did TE, now we're doing TM. So if this is the Z direction, and this is the X axis, this is region 1, and this is region 2. It's assumed that they have different values of beta. There's a beta 2. Have different values of eta. Eta 1, eta 2. Now we're talking about plane wave propagation. So what we do is this, we say, there's some bounced off, right? Like this. And there's some that goes through like this. But now we're talking about a TM, transverse magnetic. TE, the E field was perpendicular to the plane, right? Remember that it's propagating? The plane is propagating is in the board. So it's this way, TE. And I said for TE, think of it as horizontal polarization, because if this thing was laid down, the electric field would be parallel or it would be horizontal. With me? That's how they usually say in radar. Here, the H field is sticking out of the board. So now the H field itself is sticking out of the board. But in Dr. Whitmore's book, he doesn't describe the equations in terms of an H field magnitude. What he does, knowing that this is true, he puts this as some E naught incident, but he divides it by eta 1 because the ratio of E naught to H naught is eta. Do you follow me? So he does it that way because it's more convenient for him. Now, this is the H field, by the way. This is the H field. This is H incident. It's this times e to the minus j beta 1, and then there's going to be x sine of theta incident plus, plus z cosine of theta incident in the AX direction. Are you with me? Now that's the H field, not the E field. Got me on that, everyone? To get the E field, we use the old trick. We say, well, the E field incident, right, must be minus eta 1, unit vector in the direction of propagation crossed into the H field incident. Are you with me? If you're reading along in your book, what page is that on?
366.
366, and if you have your books, please bring them here if you can, and just write in your books. Look at your books. It helps. It really does. I've written in all my, but most of my textbooks, and those are the things I keep with me. The notes, they go places. Never had, I've got a couple of binders, but most of mine are scattered throughout the book. Anyway, this is equal to E incident. So what is it going to be? E incident is going to be minus eta 1, whatever it is. A unit vector in the direction of propagation. Remember how I told you to get this? You look at this, right? It's minus j beta z prime. This is z prime. You all remember this from last time? And that means a unit vector in the direction of propagation of incident wave is simply going to be equal to cosine theta incident AZ plus sine theta incident AX. You with me on that, class? Right? That's a unit vector. So I put that in here, and I have, I'll do the AX first. Sine theta incident AX plus cosine theta incident AY crossed into the H field, which is E naught incident over eta 1 times e to the minus j beta 1, and I'm just going to call it z prime because I hate writing that over and over again. So call it z prime incident, and that's equal to x sine of theta incident plus z cosine of theta incident. And just understand, I'm doing that to save, and this is incident, trying to save, this is actually, I'm sorry, this has got AX and O, trying to save the room, and this is a Y, right? It's coming out of the board, it's Y. Correct, class? If you look in your book, he has that, doesn't he?
Yes.
He'll show it. Now we're going to do the crossings here. Y'all agree with me, by the way? If I'm going too fast, bear with me. Just take a look at your book. What I'm doing here is repeating the same thing we did for TE, only with a TM operation, all right? It's the same exact steps I did for TE. All right? Now, when we do the cross operation here, what happens?
Your y components go away.
Well, we have AX crossed AY is,
AZ.
thank you. So I'm gonna put an AZ here, right? And then we have AY cross, wait a second. That's AZ. Ah, sorry guys, that's AZ, my bad. AZ crossed AY is minus AX, thank you. So it's minus right here, and that's AX. Then that goes away, and that's your field. Now you can structure it any way you want, but you can see the 8 of 1s cancel, and you have that. Y'all with me? You can put the E naught out in front if you like, they do that. I put the actual vector directions out in front. Y'all see it? Got it? Good, don't trust me. Make sure it's right. I appreciate it. So that's gonna be the incident field. This is the incident H field, incident E field, right? You all see now, just think about this. When we go into region 2, what changes? Beta, eta 2, and the angle here. Let me put this down. This is the angle of incidence. Y'all realize the angle of incidence is the angle of reflection, class? Remember that? So this is really theta incident 2, which is nice. But we don't know this. This is theta transmitted. We can get that from Snell's law, right? We can very easily get that from Snell's law. I'm not gonna do, yes, sir?
That theta incident is equal to theta reflected unless you're for lossless media, right?
I'm not absolutely certain, but I think it's generally true. The reason I say that is because Snell's law is true for all media. Look at Snell's law, right? Remember, beta 1 sine theta incident is beta 1 sine theta reflected. The only way that's true if actually the theta is the same.
Right.
So I think it's generally true. I'm just gonna say that. But I always get nervous when they get some wacko kind of numbers, when they get imaginary numbers for beta or something, or when they talk about any kind of length contraction, like relativistic effect. So don't get me on that one generally, but
Right.
if you find one in this class that isn't the same, bring it to my attention, I'll be shocked. All right, we've got these two. Now I'm gonna tell you for the transmitted field, identical, except for the angle, eta 1 and beta. I can literally go down here and say the transmitted field will be equal to E naught transmitted, and I can just put it as E naught incident right here, times tau. Well, no, I'll put the transmitted field. I'll leave it as the transmitted field here, divided by eta 2 times e to the minus j, and now it's beta 2, and then it's x times sine of theta transmitted plus z times cosine of theta transmitted, and it's in the A, that should be y direction, the AY direction, it's coming out of the board. That's H transmitted. E transmitted will have the same form. It will be I can make that minus, make that plus, like that. And now it's going to be equal to cosine theta incident AX minus sine theta incident AZ times E naught transmitted e to the minus j beta 2, that better be a beta 2, yeah, x times sine of theta transmitted plus z times cosine of theta transmitted. That's the transmitted field. With me? Everybody see what's going on here? Now, when we go to get this field, I want you to, this is the reflected H field and reflected E field. Take note of this. Y'all see it's still going in the positive x direction, right? Y'all see that? But it's doing what? It's going in the minus z direction now when you're up here, right? The reflected wave. Y'all agree with me? That's something to take note of. It has the same value of beta, beta 1, same value of eta, eta 1, right? And it's going to have the same frequency. Everything else is the same, including the angle, by the way, because theta incident is theta reflected, except the direction, the z direction. So what I can do here is say that H, I'm going to just put this on here, H reflected. Now look at the book on this one, and the reason this is the case is because the reflection coefficient is determined in terms of, it's the ratio of E naught reflected over E naught transmitted, not H naught reflected. You got me on that one? And because of that, you're gonna get a minus here. This, for some people, might not be able to see it, so let me put it up here so everybody can see it. Here you're gonna get H reflected, and that'll still be equal to E naught reflected over eta 1. Now that is simply the magnitude of the H field, the ratio of E to eta. You're gonna have an E to the minus J beta 1, but now it will be plus X times sine of theta, X times theta reflected, but now it's gonna be minus Z times the cosine of theta reflected here. All right? And the reason it's minus is the wave is going in the minus E direction. Can you all see this, class? And that's going to be AY. Technically to get E reflected, it's minus eta, right? And then it's unit vector in the direction of propagation of the reflected wave crossed in to the H field. Now I'm just going to tell you the eta will cancel. All right, and you're going to be left just with E here. But what really happens when you do this, if you come down to it, we'll put this down here. E reflected will be equal to minus eta 1. Now a unit vector in the direction of propagation. I know I'm talking a bit fast, but this is redundant. It's the same thing we did before, except what? Now we're talking about the H field that's perpendicular, not an E field. That's the only difference. So when I look here, the unit vector in the direction of propagation will be equal to sine theta incident AX, but it will be minus cosine theta incident AY, or AZ, pardon me, AZ. Y'all agree with that? Take a look. And now that's crossed into the H field. Well, the H field itself was there, so it's E naught incident over eta 1, E to the minus J beta 1. How about I leave it as Z prime reflected and AY? And the only reason I did this Z prime reflected, because this, I keep on having to write that, it gets irritating. It's just redundant. Y'all agree with me? What page is that?
366.
Still 366. Everybody got that? Now, when you turn the crank on this one, you may get a problem, not today, but you'll get one at some point, where you actually have to go through this, but I will give you the tools, you might say, to do this. I'm not going to expect you from scratch to do all this stuff, because I've been around too long, and it takes a while for this to really sink in. All right? But if I do this now, let's go through it together. Let's take care of the vector. AX crossed AY is AZ. So I'm going to put an AZ there. Then AZ crossed AY is minus AX. So that means this plus, and that becomes AX right here. And lo and behold, you also notice the etas go away, don't they, class? And if you look in your book, you're going to, you know what? I'm sorry. H reflected. I didn't do this. This has got a minus sign. I'm sorry. This makes that plus and that plus. There we go. I'm sorry, but he has it in the book. He defines, because he defines the H field as minus E naught over eta 1. Do y'all see that?
Yes.
Okay. I'm sorry. I'm telling you that. This is going to be positive. Now, after that, just for the record, we go and get the reflection and transmission coefficients. Do you understand? The way we get them simply, listen to what I'm about to say, because it'll help you later. Whenever you're doing reflection and transmission coefficients, what you always want to do is find an equation that's generally true that's the easiest to solve. Now I want you to look at these equations. I got this, I got this, I really got transmitted, I got incident, I got reflected. We know that the tangent field in region 1 is E tan in region 2, and H tan in region 1 is H tan in region 2. Do you all agree with that? In region 1, you have two fields. You have an incident and reflected field, right? If we look at the E field, it's tangent. I want you to look at this. The way we're going to get it to make life easy, please hear me when you do this. Set Z equal to 0 and X equal to 0. Now, why did I do that? Because that eliminates all the information in the problem that's not necessary. Now I can come here to E incident right here, and I can get rid of this, right? You follow me on that? If Z and X are both 0, that goes away. That goes away. And that goes away. And what else goes away? This. And that. Now, it's a lot easier to do. When I talk about H tan 1 is H tan 2, what is it? Well, this is the tangent field. This should be a minus though. This is the tangent field in region 1. Is it not, class, for the H field? It's in the Y direction. Y'all follow me on that? Give me a show of hands, how many do? Tangent means, when I say what is tangent to something, if you talk about this table, it's any vector where the entire vector length is in the tabletop. That's tangent. Perpendicular is something where nothing of the vector is in the tabletop. It's not, that would be perpendicular to the tabletop. Follow me? So when you look here in this region, if that's Z and that's X, well, tangent is anything that has an XY component, correct? And perpendicular is anything that has a Z component. That's all AY, that's all AY. They're both tangent. So I take this plus this is equal to, wait, hold it. H incident plus H reflected. Let me just do this. H incident plus H reflected equals H transmitted, or in this case, H incident is E naught incident over A to 1, and then H naught reflected is minus E naught incident over A to 1 is equal to E naught transmitted over A to 2. There's the first equation. The second equation has to do with the tangent E fields. Please just watch this. I'm not going to belabor this point. For the tangent E field, well, look at the incident E field here. The components that are tangent are X or Y. Do you see that? The only component that's tangent is this one. You all see that, class? I circled it for a reason. What about the transmitted field? For the transmitted field, the only component that's actually going to be tangent is going to be this component right here, right? You agree? And finally, for the reflected field, where is it?
Right here.
Huh? It's going to be this. Oops, sorry. This. You agree with me? Class? All cosines. You see that? Now, we could say, we could go ahead and add them up and we can say that finally what you're going to get, you're going to get cosine theta, that's reflected times, that's reflected, my bad, times E reflected 0 plus, where's the incident? Cosine theta incident times E naught incident is equal to cosine theta transmitted times E naught transmitted. These are the two equations. I don't have time to do this, but now what we end up doing is solve for E naught transmitted here. Just multiply this by 82. Follow me? Take this, and then take this, multiply by 82, and stick it in here for E naught transmitted. Follow me? So now you have one equation with just E naught incident and E naught reflected. You divide by E naught incident, and you get the ratio of E naught reflected over E naught incident. Follow me? And that is the reflection coefficient. That is done in the book. You can do it from here. I'm going to give you the answers now, all right? So now when we do transmission reflection coefficient, there's something very important about to happen. I'll put them down here, guys, check me. When I get the reflection coefficient for the TM wave, now I'm going to get, it'll always be A to 2, there'll always be an A to 1 here, and there'll always be a negative sign here. Then there'll be an A to 2, and there'll be a plus sign, A to 1 here. I know that, always. It's impedance you're going into minus the impedance you came from over the sum. What's different now, before with PE, that was a cosine of theta incident. For this one, it's cosine of theta transmitted, and this is cosine of theta incident. This is cosine of theta transmitted plus N1 cosine of theta incident. Follow me? That's the reflection coefficient. There's a very important thing we're about to see. Now the transmission coefficient, if you went through the math on this one, and it's good to do it at least once to prove it to yourself, you find that the transmission coefficient is going to be equal to 2, and this is the way I always tell people, just write this down first. 2 times a to 2, you know that'll be there no matter what. Then you'll have a to 2 plus a to 1, and there's going to be something multiplying. Up here, you would think it would be cosine of theta transmitted, but if you do the proof, you're going to see this is equal to cosine of theta incident. Down here, you're going to have cosine of theta transmitted, and this is going to be cosine of theta incident. Now go look in your book and see about this. Y'all see it there, class? How many have a book they're looking at or referring to? Spattering of hands. Good for you. If you brought your book, you're lucky, all right, because you can look right at it. By the way, he doesn't put this. What he does is put this down. E naught reflected over E naught incident. And he puts here E naught transmitted over E naught incident. If you look carefully, he does not do the ratio. I like to put gamma and tau. Yes, sir.
For the transmitted right there, would that be a positive or negative?
It's actually negative. Look at the book.
We don't have the derivation.
Now look at the formula.
Of the formula.
See that one? Minus it.
Right. Is that a T or an R? The transmitted.
Oh, wait a second. Wait. Sorry. This is positive. My bad. The reflected field's negative. Ugh.
Over on the right.
Oh, on the right.
I got it.
I got you.
Sorry. I apologize for that. Thank you for catching me. Now, those are the transmission reflection coefficients, right? There's one thing that happens here. How many remember in physics the term Brewster's angle? Anybody? Brewster's angle. You had optics, right?
Yeah.
You didn't have physics. Oh, no, you did remember. He does. Brewster's angle is an important angle because what it means is this. There's going to be an angle when all the wave is transmitted, even though there's an impedance difference. Did you hear that? Even though there's a difference in impedance, and your gut feel is something's reflected, everything's transmitted. Nothing's reflected. So how do we get it? We set this equal to 0. This is Brewster's angle. Write this down. Gosh, time flies when you're not doing it. If I look at this right here, I want that equal to 0, right? The way we get it is we set this equal to 0. If that's 0, if the reflection coefficient is 0, do the math, everything's transmitted. Do you follow me on that? Mm-hmm. Now that means that I have a to 2 cosine of theta transmitted equal to a to 1 cosine of theta incident. That's Brewster's angle by definition. If that occurs, instead of calling it the incident angle, just call it BA for Brewster's angle. All right? That's the angle when everything's transmitted. This is a cool effect, and it only happens for TM. It doesn't happen for TE waves, which means you can build polarization filters and things like that and just swing the thing back and forth. It'll hit a Brewster's angle for the incoming wave, and you can actually get all the information about a certain polarization, but that's later, much later. So now when I look at that, well, how would I get that actually? How would I figure out what that angle is? Well, remember, if I square these things, and he has this in his book, he has a to 2 squared is cosine squared of theta transmitted is equal to a to 1 squared cosine squared of the angle associated with Brewster's. But then I can replace cosine squared but 1 minus sine squared. Agreed, everyone? Well, if I replace this by 1 minus sine squared, now I have a to 2 squared times 1 minus the sine squared of theta transmitted is equal to a to squared, a to 2 squared times 1 minus the sine squared of theta Brewster's angle, the angle at which everything's transmitted. Now those are etas and that's sloppy. But then I can replace the sine of theta t if I use Snell's law, because Snell's law says beta in region 1 times the sine of the incident angle is equal to beta in region 2 times the sine of the transmitted angle. I know I'm flying on this one, guys. I'm just trying to get through this. Y'all agree with that? And that means if I divide this by beta 2, now I get this, right? And I can square that, right? And when I square this thing right here, and this is Brewster's angle, by the way, When I square this thing right here, I put it in here. Got me on this one? And then I have something in terms of just Brewster's angle, sine and square of Brewster's angle, and I can manipulate it. Do you all agree? At the end of the day, you'll have something like this. Theta Brewster's angle is equal to sine minus 1, and depending on how far out you want to take it, in his book, see, if you're going to allow for all type of media, it gets a little icky. But if you just assume that you have non-magnetic, and lossless region, then you're going to get 1 over 1. Actually, the way he has it written, it's going to be, he uses a square root operator. He doesn't, 1 plus epsilon relative 1 over epsilon relative. I think he does, should be a square root here. If it's not, it should be a square root here. 1, and it's plus epsilon relative 1 over epsilon relative 2. Now, I don't generally remember that, but I remember this, and I can get anything I want from that. That's Brewster's angle. Understand? It's a very important thing because everything transmits at that angle, if it's Tm. And now, for my next trick, the long-awaited quiz you guys can't get enough of, right?